Actually,
Shark boots.
Wait, weren't you electrical?
I was, yeah.
Yeah.
I kind of shifted.
I think I'm like, is it electrical artist?
Just some of the things that I'm interested in, like, back with the over.
Okay. So, homework 2 solutions are posted. Sorry, exam 2 solutions are posted. And so if you look at your exam and you compare those, if you have any questions, we could meet in an office hour to discuss them, or you bring home in class. Maybe email me and we'll try to schedule in some time as we go through things to review some of those topics, and particularly touch on things that were confusing if the solutions don't clarify it enough. Homework 9 is posted due Wednesday. Due Friday, sorry. I'll be gone, so you submit it to my office. And so in John Marie, here's my office, here's 259, and there's some slats over here, so there'll be a folder there that says 220 on it. The hallway kind of comes down around like this, down the stairs, and so there's some slats there, and so there'll be a yellow folder that says 220 on it, and you can put it in there, and I'll get that when I get back and get it graded. So ideally, we turn it in by Friday. I'll probably be retrieving it a little bit after that. So if for some reason you didn't get it done on Friday, get it in there on Saturday. But you have enough. We've covered enough material that you can do that, and we'll review some problems today. So are there any questions about the homework that anybody has a chance? I should have some email connections if you have questions over the next couple days going through those and wanted a clarification. You can send me an email and I'll try to respond as best I can. We're going to talk about kind of outline of things that are coming up, and then we're going to talk analysis of variance. We'll do an example like the homework, investigating things, a little bit this business of multiple comparisons, and then do kind of an example to introduce this idea of two-way analysis of variance. In the descriptions of the statistics course at UVM and other places, and the books that focus on engineering and the sciences, they seem to make a point of having things with multiple, two-way ANOVA, multiple possible treatments, because in a lot of scientific scenarios, you're using 2 or more factors that you can vary, and how do you evaluate that in an experiment. So we get kind of an introduction to it. There's a lot of complex designs that are out there that could be studied particularly in the next course or in the context of a particular research lab, but at least this will kind of set the base if you want to go on and learn more. So in terms of outline, we have today's class. Next week there's Monday and Wednesday. In this one we're going to look at the chapter 12, which has to do with linear regression, right, and prediction of an outcome, right, for a couple of days. Then there's an Easter break that comes in there. Then Easter is Friday and Monday for break. We're going to come back here, we'll look at some material in chapter 16, which includes things like control charts for decision making, for monitoring processes, some of that material there. So we're going to skip a few of the things that are in between. And then we come back and it's really the last week. And that's a short week as well. So Monday, Wednesday will really be review, right, and summary of things going on in the course. So pretty close to the end to get a taste of the topics and linear regression and so on. And so the homework 9 is due now, but I think homework 10 won't be due till after that. We'll have a couple of lectures on linear regression and prediction correlation here. And so I would make it due on Friday, but we're not meeting on Friday because of the break. So we'll make it due here. There'll be a homework that discusses some of these things with control charts. That'll be due in this area, and that'll be it for the assignments, right? The other thing you have going on, of course, simultaneously is the project. And then there's a final, right, for the course. And we'll, starting probably on this Friday, make sure that the material is available so you can study for that. And you'll get at least a sheet of paper for some notes. It's a little weighted towards the end in terms of methods, but it's kind of takes a little bit from all the parts of the course, right? Or the inference. So on Friday, when I'm not here, you have time to finish up that homework. That is due then, but you have time to think about the project. Right? Is there a data set you want to look at? What would be some hypotheses or interesting questions you'd like to look at with that? Can you get the data? Yeah.
Is the outline of the project online? Like,
there is a handout, yeah, about the project that's on, so under the assignments, under the project folder, there's that describes it. Yeah. I think for a lot of people, the most common way to go about that is to take a data set, a larger data set from the book or from some other source, analyze it, describe it, so kind of a structured report. Not terribly long, but it takes some thought to putting it together so it's interesting. Yeah.
Do you know any websites we can find data sets on and stuff?
So yeah, so there would be some described in the book, and if it kind of depends on what type of topic area you're interested in. So here's under assignments here, under the projects, this thing is posted here. And when that shows up, there were a couple of links in there to data sets. I have a number of, there were some online sites, so if there's a kind of a data set described in here, and I would need to take a little time also to go through to look at the different data sets that are described in this. They don't have a separate section in this book, right, about those. So some of them that we didn't use for a particular problem or something, but if they're described as part of those things, I can send those. You don't just have to type in those large numbers of values. And this seemed to load in here. There was a link to maybe this one will show up. Well, we're just going to let that go. There was a link there to a book. It's in the biological sciences that has some data sets that are there. Another relevant site is this NIST book on Engineering Statistics Handbook. So within this, kind of in this Explore, there's a few case studies of different things. So here's fatigue, life of aluminum alloy. So there's some background of some of these things. Here's some data that are included in some of these. They actually have some R code for doing these things. So you can look at that site. That would be a place where you might get some data and some guidance about the R code. You would want to write it up on your own, but that's a fine place to look for examples and then put things into your own words, use your own analysis on it. So
you said it's like a report. How long is the report?
What did I say in that? Was it 4 to 6, 3 to 5, something like that? But once you start including graphs and tables, and some reports will get a little bit longer if you include a couple more graphs. But you're thinking about mostly 2 to 3 pages of kind of core text with some, things like that. You could have 5 pages of text, and if you want to include some more graphs and put a couple pages of computer code just to kind of document your work and have a record for yourself, then you could go ahead and do that. So, yeah.
Would you prefer to know what we're doing our project on before we do it?
so shoot me an email saying I found a data set. It's just a way for me to check on that you're making progress toward it. Yeah, but you're welcome to ask more questions. I'll probably try to have some more office hours over the next couple of weeks just for more study and review and so on. Yep. Okay.
Could you work with someone, or?
You can work in pairs, right? If the paired projects would be a little bit longer, and so in a number of these things, if you're looking at a data set and doing a confidence interval, or maybe analysis of variance, if there's multiple treatment groups, there's some different things that can be done. And if there's different outcome variables, then one member of the pair can do a couple things with one outcome variable, and the other person can kind of do similar things for the other, and you write it up together. But so that, or somebody who does a couple of these, tests and confidence intervals, and somebody does another statistical procedure, and you combine it so that there's a lot of ways for people to work together on those. Okay? So that's kind of the outline of things to come, and you can get the notes from that. And so we're going to look at some examples with analysis of variance, but I like to point out here kind of this overall perspective of what we're doing with the statistical inference to kind of tie it back to the earlier things, right? So really we start out with some research question, something that you want to know that's of importance for society or for some process or for business or something that's going on. Could be describing a population or seeing the active difference of different treatments. We do something to get data, whether it's observational or through a designed experiment. Designed experiments, you think about what levels of different of treatments you might compare. We're going to look at second versions, second factors that might be included, and you're going to look at all combinations. And there's once you get the data, we typically describe the data, looking at numerical summaries, looking at graphs. See what's there. Sometimes that's very good for checking the data to see if there are errors or unusual points, but it would relate to the research question you're interested in. And then there's some statistical inference. Making confidence intervals or hypothesis tests appropriate for the data. And after doing that statistical inference, there's some conclusion that'll come, about the research question. It might be that things are ambiguous and you need more data or you need to do another experiment, and sometimes it'll be, a stronger conclusion one way or the other. But in the statistical inference, we've seen data come in a number of things. Independent samples, maybe matched pairs samples, quantitative data, categorical data, and so a number of things here influence what type of statistical inference you can really do. Really, the inference method that you're going to do is influenced by that original design of the data. So the inference method depends on the design of the study. You really have independent groups, or was there some type of pairing or matching going on? What variables are you actually recording? Are they quantitative? Are they categorical? What would you do? Sometimes what exactly would you do, relates to sample size. If you have a large sample, averages and many other things are roughly normally distributed, so you can use those methods. But in real small sample sizes, people are concerned that normal approximations don't work so well, so there's exact methods or non-parametric methods and alternatives. So all those factors kind of figure in to how you're going to set things up. And that's relevant as we start thinking about analysis of variance and moving beyond just one factor. Yeah?
And there's no presentation involved, it's just a hand-in project. Right?
Yes, for this class, yeah. So it's This class is almost small enough that we could do that, but to have everybody do that, it would take 2 or 3 class periods. Yeah, so it would be nice to do that, but it's just a little bit too tight.
How about instead of a final, we present it?
We get a bonus too, so.
Oh.
There you go. Negotiation, that's good stuff.
Maybe we could, well, I'll take it under advisement. I don't know, we'll be able to change, but you know, yeah. But it's,
We're at
yeah.
the end right now, so.
So good. So what I wanted to do is look at an example or two today that are kind of like the homework, so that if there's any questions on the analysis there, that we can look at that. And so both of these examples are actually from another textbook. I thought I'd show you an example outside of our book. And the BD is a different textbook on this. And so there's one data set there and talks about the hardness of welds from 4 different fluxes. So 4 different ways that the chemical mixture is put into the weld and the speed at which these things happen, as I understand it. And there's a measure of hardness that are there. Right? And so the 4 different fluxes or treatments are just called A, B, C, or D. Right? And it might be nice to have more details about that, but that's as much as presented in this. Right? So these would be real alternatives that could be used in the manufacturing process. And these are the measurements that are in each of these. Right? So they each had 5 measurements. Not a large experiment, right? But perhaps enough to see if there's a real difference between these different methods. Right? So putting these things together, A, B, C, and D, I just entered the numbers. It'll be nice to have them all together. So this X is going to be the A values and the B values in C. And I'm going to have something that indicates which group it is when it's the next long list. And so this rep function is kind of this repeating function is kind of a very flexible thing to set things up like that. So flux is going to be A 5 times, and then B 5 times, and C 5 times, and so on. And then I put it all together as a data frame. You can just probably put just X and just flux, and it will keep those names. But you could change them if you wanted to. And so my data set is that, if I look at the whole thing, right, is my X values all in order, and then the fluxes, these 4 different things there. And so that's what the full data set looks like. Right? Not too hard to type in that amount of stuff. For this analysis, I'm going to attach that data set. The virtue of doing this is I don't have to do that $sign to refer to the outcomes. And so data frames, oh well, so it's there. Right, so we have our data. We're doing this randomized experiment. Hopefully they did something like, really randomize the order of doing the welds, or took material and kind of, they didn't do all the A's and all the B's and all the C's. Because, there could be some kind of a confounding there if there's some time variation in materials as well. So we can look at the means. You could just type the mean of A and the mean of B and so on. But this little split function will split all the X values according to the fluxes. It creates a list, actually. So this one creates a little list where there's the A's and the B's and the C's and the D's that are there. And this splits it out, and then this type of apply calculates the mean, calculates the average for those. So as a first descriptive part, does it look very much like there's some differences there. Maybe those are significant or not. But the question we want to ask in the statistical inference is, are those more than just chance? Is it just, we could look at the standard deviations of each of these. Yeah, they're not too different, right? One's about twice as much as the other one, so they're not exactly equal, but I wouldn't be too concerned with that. If one of these was 90 and the other one was 5, you know, it would be quite different. For data this size, R has something called a strip chart. You know, there's different things like dot plots and so on. What this thing will do is make this little plot here. Right? And so it actually shows you the different values. So here's the values of A, the values of B, C, and D. And so here's the 5 values there, 5 values. This looks like 4, so maybe there's a tie. And then 5 values there. So you see that there's a little difference between some of these different factors, right? Not any huge outliers there. It's hard to judge normality based on just 5 observations, but it doesn't look like any massive outliers would be there. So, because we have the 4 groups instead of just 2, we're going to use ANOVA, analysis of variance, instead of T procedures. Right? And so if you do the analysis of variance, it gives you the degrees of freedom, the sums of squares, mean squares F, and then this p-value out here. Right? So our null hypothesis we're testing, right, in this analysis. So our well example. We have the null hypothesis that the average hardness, the average strength, right, is the same in all 4 cases. Versus an alternative that there's some use of I, one of those is different. All 4 could be different. It will be one that's different from the others, right? All those different cases, just some difference out there. And so we're calculating this F statistic, right? It has a certain degree of freedom based on the experiment. There were 4 groups, so there were 3, and there were 20 observations in all, so 20 minus, so 4 minus 1, and then 20 minus 4 is 16. So it has those degrees of freedom. The statistic that this calculates is 3.87. And so the p-value is calculating the probability. We're at that F distribution. This is kind of the F distribution with 3 and 16. And we get this value out here, 3.87. And the probability we're bigger than that is that p-value. So we're kind of getting closer. Right, so this tail area out here, according to the output, 0.029. 0.029. And if that's small, then we've rejected the null hypothesis. Because the p-value, that tail area 0.029, is less than our usual 0.05 cutoff value. And so it looks like there is some statistically significant difference among the means. We saw that there was some difference between the means, and so this is 5.
So the .029 came from, again?
That came from this, it's this tail area up here. Right? And from this output, it's this value that's in here, 0.029.
That's the p-value.
That's the p-value, right.
Okay.
So we just, to get the difference in means, we did an ANOVA to get that? So we just did a difference of all the means with that ANOVA test?
Yep, it tests all 4. Are any of these different? Right. These encoded in the sum of squares residuals or error, sum of squares flux, to sort according to that, according to the different formulas that we see for that. So it looks like it's statistically significant. There is some differences, right? Another plot of those besides that strip chart would just be a box plot. Right? So this is a box plot of those 4 groups. You know, as you get larger data sets, that Stroop chart becomes kind of messy, noisy, and this kind of a summary might do. So it looks like that, yeah, although that the groups aren't totally separated from one another in terms of all their values, there's a little bit of overlap. At least one of these groups looks different, right? So then the question becomes, which one? Which groups are different from each other? Which ones stand out? And this is just a little bit more about that computation. So we got an F value of 3.84 in here, 3.87, sorry, with the degrees of freedom 3 and 16. This P, the probability, this thing calculates the probability as an F is below that value, and that upper tail area is just 1 minus that. So our p-value that's reported there is 1 minus that. You could also look at the cutoff values, right? What F value cuts off the upper 5%. What's the 95th percentile? Well, the 95th percentile of an F, 3 and 16, is at 3.24. But we're bigger than that. Right? So we're bigger than that cutoff. So our p-value is smaller, and we reject. Can we reject this 99%, the 1% tail area? Well, the 1% tail area is at 5.29. We're not quite that far out. We're kind of in between there, like we've seen. But we might want to say things about an individual treatment using a certain flux in the manufacture of these. So you can do confidence intervals for each mean. There's actually a confidence interval formula. And this is a little bit, to make this work out, this is a linear models command where you're predicting the x based on the levels of flux. And this little -1 in here means don't estimate a separate intercept. So linear models, you can ask if you need to describe 4 groups, you can give the overall average and 3 deviations, and that gets everything. Or you can give all 4 averages. And this is a little coding syntax to make this work out. But anyway, there's 4 intervals that are there. So you run that, it does that. But if you wanted to see how those intervals are made, right, in the ANOVA models, there's this common variance, right? This ANOVA model, this linear model, says that the x's in the group are equal to their means plus some error terms. Okay. And these errors are supposed to be normal around a mean of 0 and a variance of sigma squared. And so there's this error variance that's part of the model. And so how do we estimate that? The pooled estimate of that using all 4 groups together is the square root of the mean square error. And so in the ANOVA table, we had, this was in here, oh, I can't quite see it very well. Anyway, I'll look at it, it's easier to look on. This one, so the ANOVA table, where is it? Those 4 groups, ANOVA, there it is. The mean square is the square root of 63.975. And we take the square root of that, we get a number. So it's about 8, right? And so a confidence interval for each mean, a confidence interval for u sub I, just taking a 95% confidence interval for each one at this point, would be centered at the average for that group, right? Plus or minus a t value, 975, t value with 16 degrees of freedom. Associated with the error were 16 degrees of freedom. 5 groups, we're estimating, each had 4 groups, each had 5 observations, so 20 observations total, but we're estimating 4 means, so we're down to 16. Times the pooled one, and then there's an effect for sample size. Right. That goes in there. these would be narrower than doing an individual ones because we get a more stable estimate of the variance, this S&P, and we get to do 16 degrees of freedom instead of just, if we said one group, you don't have 4 degrees of freedom. That's a much bigger p-value. And so this, it's hard for me to modify that. And so actually just computing those, if we take the means times the t-value times S&P, they all have a sample size of 5, so square root of 5 is there. This thing does the minus, and the next one does the plus. And this C-bind is kind of a column bind, binding these two things together. And so it produces, running that whole thing, oops, S&P, you just define it there. And it gives the same intervals that were in that other statement. In using analysis of variance, part of looking at the data, residuals are supposed to be normal. Right? The linear model does gives us something called residuals, right? And what those residuals are, checking whether this model seems reasonable, right? Checking assumptions. One assumption is that we have independent groups. Independent groups and observations. If there's another factor, like one person's doing all the A welds and another person's doing all the B, or somebody's doing some of them and another person's doing some, it's, that could maybe influence how things are going on. So they might not be completely the same except for the treatment levels, right? And, if you're welding things and you have, a bunch of them set out and you just kind of do them all together, right, then there could be some kind of dependence or relationship there. That would be, the time and performance on one might affect the other one because of that interaction. So that's just knowing about how the experiment was set up. How is it physically done? We assume that the errors are normally distributed for this to be, now they won't be exactly normally distributed, but we don't want them to be too extremely non-normal, right, with massive outliers and heavy skewness. And we want generally the standard deviations of those errors to be roughly the same across the different groups. They won't be exactly the same, but you don't want it to be terribly, massively imbalanced. And we can check some of those things. So this, the residuals, I guess I could say how we're going to estimate each of those, right? That the residuals that we're talking about, these errors, what these residuals are, if you take each observation minus its group mean, is the difference between the best estimate of that average and the point. The sum of squares error made use of that by adding over all the groups and then adding over all the observations that are in that group of the xij minus the x bar i's squared these residuals or errors. And so we can look at those. Right? If those look highly non-normal, if there's a massive outlier, then what we say is our confidence intervals and our p-values based on this normal model, might not be such a great thing. If we do the residuals, their normal probability plot. It's not exactly perfectly straight, right? But it can be a lot worse. A histogram of that, that's a little skew, maybe a little heavy tails, but it's not so bad that it wouldn't be. If you look at the spread of the residuals, so here I'm going to save the residuals as something. So these residuals are, some positive, some negative values that are in there, and make a plot of that. Right? And I put a little vertical line in there. they're kind of every group seems to be centered around 0 more or less. And the spread in one group versus the other is not so terribly different. Maybe it's a little bit less in this one, with more in the others, but not so extreme that we're going to be worried about it. But you can check the assumptions, you can look at different graphs and things to try and do that. And the further question goes on, are any of these averages really different from each other? Are they statistically significant? Different, right? So now that we've had a significant result, we can look at pairwise comparisons. Is A different from B? If we go back to the original data, is A different from B? Is A different from C? Is B different from C? C different from D? And so on. There's actually 6 pairs that we could look at. Right? And so if we did there's a hypothesis test. What's the difference between doing a hypothesis test? Pairs of means. This, in general, doing any comparisons are called contrasts, and the contrasts can become much more involved. If we're doing more specific comparisons, like the average of these 2, is it the same as the average of these 3? And so you can do these different comparisons. If we have just a 2-sample t-test, our t-statistic is just the difference between the averages and this pooled one from the 2 samples alone. And then 1 over n1 plus 1 over n2. Now we compare that to a t with n1 plus n2 minus 2 degrees of freedom. But in ANOVA, there are, the statistic we use looks much the same, but there's just subtle differences that get used in that comparison. Instead of using the pool for just those 2 particular samples, we have a bunch, so we're going to use the square root of mean square error as that estimate of the same thing. You have the same sample sizes. So there's that one change in there. We use a different estimate of that common error. And then the t distribution we use up is n minus I. And this one there's I groups. And generally the bigger the degrees of freedom is the narrower that t distribution is, the closer it is to normal. So we don't need to be as far out, right, to get a significant result. Right? So there's just a subtle difference there. The other subtle difference is if we're going to compare not just 2 things, because we set it up an experiment, we're going to compare this group to that group. That's our primary thing. We're going to test it at 95% or 5% significance. But we're going to test 6 things, right? The chance that at least one of those is significant becomes higher. Right? The chance that they're all not significant, 0.95 to the 6th, is smaller. Right? So if you do 6 comparisons at alpha 0.5, the probability that all 6 are not significant. Well, the probability 1 is not significant is something like 0.95, right, to the 6th, which is less than 0.95. Now, it's not exactly that. They're not really independent because different means would be involved in those other things. But it's just less. If it were independent, you just take 95% chance of not having something significant, and so on. So 1 minus probability of some type 1 error is 1 minus that. So that should be greater than 5%. So you have a bigger chance of making an incorrect choice there. Right? So multiple comparisons. Bonferroni simply divides that 0.05 by the number of tests. Right? So multiple comparison adjustment. If we have I groups, if I choose two pairs, this is calculated as I times I minus 1 over 2 pairs. And let's just call that M for multiple comparisons. We're going to take the alpha, and we want at most a 5% error, chance of making any mistake. All right, we're going to do a new alpha at the 0.05 divided by M. And we're going to reject a null hypothesis if we get a t-value. So this is comparing mu1 to mu(I) versus mu sub j for two different ones. If our t-value is greater than a t with our n minus I degrees of freedom, and so it's 1 minus, well, we take 0.05, it's two-sided, we divide that by 2, and so, yeah, that's what it is. So we take a further point out there. So in this case, with I equals 4, my number of multiple comparisons is 6. And so this is 1 minus 0.05 divided by 12. And for that little calculation out there. So it's going to be further out. And so for the practical side of these things, we're going to divide that 0.05 by that and divide it by 2. And so now that cutoff point, instead of being, let's see, the QT, QT of 1 minus 0.05 divided by 2, which is the regular one, which would have a cutoff about 2.12. Right? This one, this cutoff is about 3. So our t statistic is going to have to be more than 3 or less than -3 to be judged significant, adjusting for the fact that we're doing all these multiple tests. Right? And our confidence intervals use this wider thing here. Right? So there would be a confidence interval for A versus B. Here's a confidence interval for A versus C, and so on. And you could keep looking at those different ones. Now A versus C, right, in this picture is this one, this lower one versus upper one. That 95%, well, that adjusted confidence interval, even with this wider, this bigger multiple here for multiple testing, still goes -32 to -2. So I've taken A minus C, so that's why it's negative. If I took C minus A, it would be positive. Just flip it. Right? But that one doesn't include 0. Right? So A and C look like they're significantly different from one another. Adjusted for the fact, even adjusted for the fact we're doing all these multiple tests. So you can do individual ones if you're interested in that. And that's the Bonferroni. This assumption of just dividing the number is kind of an extreme adjustment. It's probably not exactly necessary to do that much of an adjustment, although it's simple. There's this 2p highest significant differences one that will do, what's down here? This is the command. Do differences between the groups, these big estimates. Here it did C minus A. It gives a lower and upper confidence interval. They're just a little bit different than the ones we got because it uses a slightly different way of doing the adjustment. But with a small number of comparisons, 3, 4, 5 groups, it's pretty close. And it gives an adjusted p-value. So even with that adjustment, the p-value for testing is still less than 0.05, and it looks significantly different. But that is the difference. And so this gives all these pairwise comparisons. If you used just the regular 95% one, your intervals, instead of going from -32 up to -2, it goes from -28 up to -6. It's narrower. There is kind of a substantial adjustment that is made there, but most people would think of that as trying to be fair. So reporting and claiming that you're a 0.05 level significance. So the assignment basically asks you to do some things like that. But any questions about this type of thing? The things then get interesting when you have something else. So the extensions, you can have two-way analysis of variance. So we're still interested in quantitative outcomes. And in this case, you can have treatments or groups defined by some first factor, and you can have treatments or groups defined by a second factor. And each person, X, I, J, K, is going to have some level of the first factor and some level of the second factor that's in there. So you're going to choose one of the A levels and choose one of the B levels, and that will give us two factors simultaneously. And if there are I levels of this first one, and there are J levels of the next one, this index K would be the number of subjects that have the simultaneous, the same levels, have levels A and B in there. And so you could look at, for all subjects at levels, I'm going to kind of switch here and not use that A and B anymore, but just kind of I and J. So there are ith level of the first one and the jth level of the second one. We can have an average of that group. And you can an average of all the points that are in there over all those. I guess the K is going from 1 up to the number of subjects there. And we can look at residuals. So, the difference between the residuals or errors. You can do Xi, J, K minus its group average. It's got a two-way group average. And in two-way, we won't go through all the formulas in detail for two-way ANOVA and these other variations. But the sum of squares error is a sum over all the I and J factors, kind of all of those pairs, and a sum over all the individuals of the Xi, J, K, the values minus the averages between the groups squared. And if all the groups were combined, and we didn't have any differences at all and put everything together, the sum of squares total in the analysis of variance, we can add over all the subjects, I levels, J levels, individuals of those things, minus the overall average. We have 3 dots in our book. So this is the overall average. And between the sum of squares total is decomposed as it did before. There's a sum of squares error term, but then there's a version of these things that give the sum of squares for the treatment, the A treatment. There's a sum of squares for the B treatment, And there's a sum of squares that has some interaction. And those separate things that there's the effect A has, the effect B has, and the interaction between those, what effect it has on X gets put into the model. And so it's a lot of notation and things to go through. Let's look at an example. So the second handout today shows up here. So this is again from NVIDIA, right? So it's measuring a yield of a chemical process. So you're putting in a catalyst and a reagent, different levels of a catalyst, different levels of a reagent, and then getting an outcome. Right? And so the X values, these are the values of the outputs. And we have 4 levels of A. So our example here. We have catalysts, A, B, C, and D. And we have combined that with some different reagents. R1, R2, R3. And so there are 12 groups in all. Where each group is defined that you put one of the catalysts into the reaction and you put one of the reagents into the reaction, and you see what comes out of it. And within each of these things, 5, 1, 2, 4. Is that right? 1, 2. I typed 4 numbers there. There are 4 measurements. Right, so there's 48 measurements total. And we're interested, is there an impact of the A, does the catalyst make a difference? Does the reagent make a difference? Is there maybe an interaction between these two things where some work better together and some pairs don't really produce the high yield that you would like? Right? And so an analysis, two-way analysis, enter the data. Right? And so if you go through this, here's A1, A2, A3. So that's the A catalyst with reagent 1, A with reagent 2, A with reagent 3, and those are the 4 measurements. And here's the B's, here's the C's, and here's the D's. So the reagents all, so the X's all put together is this. So here's my full measurement of X measurements that come in this experiment. There are some catalysts. Right? So the first 12 of these, right, are all A's. The next 12 are all B's. And so this catalyst vector will set that up. So catalyst from this command here just gives me a bunch of A's, B's, and C's, and so on. Reagents, I'm using kind of a repeat within a repeat. So I need to do reagent 1, 2, 1 4 times, and then 2 4 times, and then 3 4 times. And then I got to do it again. So this part here sets up just 12 values. But then I need to do that for every catalyst. So I need to do it 4 times. So it's repeating, something repeating. In any case, I put all that's X. My two-way data has my X, my catalyst, and that. Right? I'm going to attach that. Up here in this environment, it shows these things. And so the two-way, if you click on it, it gives you a little spreadsheet picture up here. Right? So here's the X outcome, the yield, and then my 2 experimental settings. And, right. So, I'm going to attach that so that I attached it, okay? So, it's easy to refer to the variables of catalyst and reagent. There was 4 measurements in every cross category, so good to check that if that's what you intended, that's what you get. The means by catalyst. It kind of looks like one of these catalysts is doing better than the others. Maybe the other ones are not doing any different than one another. Reagents, kind of these couple of reagents seem to be a little bit better than the other ones. This paste is kind of a little tricky thing, right? Where you're going to take the catalyst variable in that one and just paste the names together. Right, so I'm going to paste the A, B, C, D with a R1, R2, or R3. Right? And so what that produces for me is AR1, or a bunch of AR1s and AR2s, AR3s. So I can then split up all the X's by these smaller groups and look at the means there. And if I do that, I get this result. So there's some of the combinations, like A with R2 got 89. But C with R1 is quite a bit lower. You could look at kind of the distribution by catalyst. Here's the A's, B's, C's, and D's. It looks like the A's are quite a bit higher. Box plot worked with this size of data too. A is bigger. None of them look too skewed. There's a little bit of skewness in there. It doesn't really mark any as outliers as things. So it's probably going to be pretty good for our assumptions about ANOVA. You could look separately for the reagents. These three different things for reagents don't seem to be quite as different. A little bit more overlap. And box plot shows there it is. Right? They kind of overlap more. Maybe there's not as much difference by reagent, but maybe so. If you split it by these, you can get box plots from all these different categories. And this is a just look at it real big. Let me try to rerun that. If I can. Can't quite see all, but these are the A's, the B's, the C's, and the D's. So in interactions, so B seems to be doing differently based on which group it has. And C seems to be different based on which reagent. But that's not so much there for A, not so much there for D. It's not kind of a, if they were all kind of sloping up like that, right, there might be kind of a different, I don't know, there might be some way that they're influencing each other. A little bit hard to see.
Like the way A and C are, B and C are acting?
Yeah, so B
Reagents.
and C is kind of going
Yeah.
up depending on which, so there's a, the B seems to work better for the third one, and C seems to work better for the second or third. But it's not necessarily the same for A and D. That it doesn't seem to be quite equal across. So it's kind of maybe a suggestion there's an interaction. To do analysis of variance with this interaction in R, our X is modeled as a function of catalyst times reagent. In the R modeling, this will give you an effect for catalyst, an effect for reagent, and then an interaction. So if you run that whole thing in here, you get this table. So you get degrees of freedom, you get sum of squares, mean square, and you get three different F statistics. You get an F statistic for testing the catalyst reagent interaction, and then you get ones for these main effects. Now it turns out that probably with these real small sample sizes, that the interaction doesn't end up being significant. We see kind of maybe some suggestions there, but it's kind of inconsistent across, well, anyway, it's just kind of a small sample size to see that. And sometimes it's present, sometimes it's not. So this p-value is not significant. So we would judge based on that there's not a significant interaction, there's not really evidence of an interaction between these things. The thing you can do then is do an analysis variance where you take that one out and just have a catalyst plus a reagent. And that table then just has a main effect for catalyst, a main effect for reagent, and both of these things look statistically significantly different. And in one experiment then you've really learned about two different things. You've learned about the catalyst and the reagents. If you just picked one of these, picked one reagent and then tested all the catalysts, or picked one of the catalysts and tested all the reagents, you might still have got significant results, but it would have been less efficient. In this, you get tests of both. You can also say that the test about the catalyst, it's going to average over these different reagents that people might use. So if you had to recommend a catalyst, probably that one that had the A that had the highest, right? And then that went out into the world as the recommendation, but people used different reagents based on what they had available, it would kind of average out and be statistically significant. But anyway, this is we're kind of running out of time, but that's kind of a brief example of how you can put multiple factors into R and do that. And so, one project would be to take an example that we haven't done that concerns two-way ANOVA and kind of think about that, read a little bit more into the textbook and write a summary of analysis along those lines. Well, that's enough for today. I'll be away, like I mentioned, so you submit the homework to the folder outside my office, and I'll see you next week.
Here's the
Okay, good, thank you.
Yeah, I'm sorry I was late. I overslept again. My boyfriend handed me food on the way over, so I swear I didn't just stop at Einstein's and wait for 20 minutes. So
Other things came up. Well, thank you for being here.
Yeah.
Being here to me.
So when are you leaving?
I'm leaving on Thursday morning.
Okay. All right.
But I'll have some email contact
Okay.
over the weekend.
Yeah, I like emailing you just because I'm going to be watching the last Integrities as well.
Okay.
But in case there's anything that's not sticking as well, and then
Okay.
I just email you a question or two.
Sounds good.
Also, can I have my nip up? That's good. I just know someone else's exam. I laughed at the fact I got one.
Oh,
Like, I literally was laughing to myself when I saw that. I'm like, really? One point? No, I was so mad because I was good till question approximately four,
Yeah.
and then I realized I didn't write the formula down for that one. I'm like, I was so mad. Thank you for giving it back because
But I
I need.
printed out the exam to be taken.
Okay, yeah.
Right, this is just the original that I dropped off.
Ah,
I don't know if it's
okay.
Yeah, thank you for giving me.
Sure.
So we have class tomorrow? So.
No.
No, okay.
Yep.
Okay.
So do we not have class on
Thank you.
Friday then?
No class on Friday.
Oh, cool.
But either way, it's been in and so it's a build as a project day. You can
Yep.
focus on the project. I'll try to get some. I mean, we'll be looking ahead at regression, but there's not a great. Finish this homework, think about the project, and then if you wanted to look ahead in the section on regression, you do that for a couple days.
Okay. And in 251, I assume it's same kind of outline for the project, except something more in depth, because I wasn't there for when you described the project.
Yeah. So it's posted
Yeah.
online.
Right.
I don't have it with me, but
Yeah.
I only got
So it could be
3 weeks.
taking
I only got
a topic and you look if you haven't talked about it as much, or taking a topic and applying it
Mhm.
to a data set that you can put looks like.
Bye.
Bye.
Have a good weekend.
Thanks, you too. There's some other options there.
Okay.
So since you're taking the 2 classes, maybe doing something where you are doing inference for a data set
Right.
here, but then you're interested in how it performs. So maybe you do a simulation to kind of check assumptions.
For 250. Okay.
251, because that would be involved random number generation.
Right.
And
Perfect.
so
Okay.
there could be a way to integrate them.
Okay.
And make them just kind of reinforcing each other.
Right. Okay. Thank you.
Yep.
I think I'm going to try and get in contact with my old research professor because she was seeing if she would allow me to use some of the data we found over the summer for the project. Would that be okay? Since it would just be a data set that I
Oh,
just
sure,
be
sure,
analyzing
sure,
it.
yeah.
The only thing I don't know about is how normal the data would be because we're looking at brain cells. So
But you know, that could be interesting as well. So if some brain cells, if it was very skew, you know, you could explore doing a t-test or confidence interval on the original